Have you ever wondered how the sun, the blazing star at the center of our solar system, came into existence? It all began roughly 4.6 billion years ago, with a seemingly ordinary molecular cloud in the vast cosmos. This cloud, a colossal mass of dust and gas, was destined for greatness as the birthplace of our sun. When the gravitational forces within the cloud became too strong, a collapse was inevitable. This gravitational collapse, a cosmic domino effect, led to the formation of a dense, hot core known as a protostar. This protostar was not yet the sun we know and love, but it was on its way. Over time, the protostar continued to grow, accumulating more and more material from the surrounding cloud. As it did, the pressure and temperature at the core escalated, creating a hotbed for nuclear reactions. The immense pressure and heat at the core of the protostar drove hydrogen atoms to come together, fusing into helium. This process, known as nuclear fusion, marked the birth of the sun as a star. Nuclear fusion is not just any reaction, it's a powerhouse, releasing a tremendous amount of energy. This energy is what gives the sun its radiant glow, its warmth, and its life-giving properties. So there you have it. What started as a humble cloud of dust and gas underwent a series of extraordinary transformations to become the sun, a radiant orb of hydrogen and helium. It's a process that took millions of years, guided by the fundamental laws of physics and the relentless force of gravity. But the story doesn't end here. The formation of the sun was just the beginning of an epic journey that continues to this day, as our sun continues to burn brightly, fueling life on our planet and captivating our imaginations. Thus, the sun, a radiant orb of hydrogen and helium, was born. What lies beneath the sun's fiery exterior? An intricate structure of layers, each playing a vital role in the sun's energy production and emission. At the heart of it all is the core, a region of unimaginable heat and pressure, where temperatures reach over 15 million degrees Celsius. This is the sun's engine room, where hydrogen atoms are fused into helium through nuclear fusion, releasing an incredible amount of energy. Wrapped around the core is the radiative zone, where energy generated in the core begins its outward journey. Here, photons, particles of light, embark on a random walk, bouncing around for thousands, perhaps even millions of years before they reach the next layer. This is a realm of intense heat and dense plasma, a kind of stellar soup of ionized atoms. Next comes the photosphere, often referred to as the sun's surface. This is the layer we see when we look at the sun, the source of most of the light and heat that reaches Earth. It's a relatively cool layer, with temperatures dropping to about 5,500 degrees Celsius. Above the photosphere lies the chromosphere, a region of glowing plasma. It's this layer that gives the sun its red color during a total solar eclipse. And beyond the chromosphere, we find the corona, a mesmerizing, ethereal halo of ionized gas that extends millions of kilometers into space. Although it's the sun's outermost layer, the corona is surprisingly hotter than the surface, reaching temperatures of over 1 million degrees Celsius. From the core to the corona, each layer of the sun contributes to its radiant glow and the heat that warms our planet. These layers work in harmony, generating and transporting energy through a complex process that ensures the sun continues to shine, fueling life as we know it on Earth. This layered structure enables the sun to radiate its life-giving energy to the far reaches of the solar system. Why is the sun so crucial for life on Earth, you may ask? Well, it's the sun's radiant energy that fuels photosynthesis, the process that plants use to convert sunlight into food. This lays the foundation for all terrestrial ecosystems, making life as we know it possible. But the sun's influence doesn't stop there. Its warmth drives the weather patterns we experience daily. It stirs up ocean currents and orchestrates the circulation of our atmosphere, shaping the very climate that governs our planet's habitability. Solar radiation, too, plays a pivotal role. It's the force behind solar panels, a source of renewable energy that's becoming increasingly important in our quest for a sustainable future. So you see, the sun is more than just a brilliant light in the sky. It's the engine that drives life, the heart that keeps our world beating. The sun, in essence, is the engine that drives life on our planet. How has the sun been perceived throughout history and studied in modern times? In the tapestry of human culture, the sun weaves a thread of brilliance. From the ancient Egyptians who saw it as the god Ra, to the Aztecs who offered it sacrifices, the sun has been revered as a divine entity in many civilizations. It symbolized life, power, and cosmic order, its rising and setting weaving the rhythm of days and seasons. Monuments like Stonehenge in England and the Sun Temple in India stand testament to this celestial reverence. Their structures aligned with the solstices and equinoxes, marking the sun's annual journey across the sky. But the sun's role in our lives extends beyond the realm of myth and symbolism. It is a scientific marvel, a natural nuclear reactor that has ignited the curiosity of modern researchers. In the realm of solar physics, scientists probe the sun's magnetic fields, sunspots, and solar flares. These studies aim to unravel the mechanics of solar activity and its potential effects on Earth. The advent of space technology has further propelled our understanding. Telescopes, satellites, and spacecraft like NASA's Parker Solar Probe have journeyed close to the sun, sending back invaluable data about its composition, structure, and behavior. This information not only deepens our understanding of the sun, but also of other stars and the broader cosmos. Moreover, the study of solar activity informs efforts to predict and mitigate the impacts of space weather on our increasingly tech-reliant world. Solar flares and coronal mass ejections can disrupt telecommunications, power grids, and satellite systems, making solar research vital to maintaining our modern infrastructure. From ancient reverence to modern research, the sun continues to captivate our curiosity and command our respect. It is a testament to the enduring allure of the cosmos, a beacon of light and knowledge that continues to guide us on our quest to understand the universe and our place within it. What spectacular shows does the sun put on for us? The sun, our radiant star, is a theater of cosmic proportions, staging a myriad of breathtaking phenomena. One such spectacle are solar prominences, immense loops of plasma that erupt from the sun's surface, tracing the paths of intense magnetic fields. These fiery arches, larger than our entire planet, can persist for months before collapsing or erupting, casting plasma into space in a dramatic display of solar power. Then there are coronal mass ejections, or CMEs, massive bursts of solar wind and magnetic fields that are hurled into space at high speeds. When these CMEs collide with Earth's magnetic field, they can trigger spectacular auroras, painting the night sky with vibrant hues of green, red, and purple. And let's not forget the total solar eclipses, when the moon perfectly aligns between the Earth and the sun, casting a temporary shadow and offering a rare glimpse of the sun's elusive corona. These celestial events serve as a reminder of the sun's awe-inspiring power and beauty. What will happen when the sun exhausts its nuclear fuel? This question has intrigued astronomers for centuries. The answer lies in the distant future, a future where our radiant sun will undergo a dramatic transformation. In about 5 billion years, the sun will have exhausted the hydrogen fuel in its core. When this happens, the core will contract under its own gravity, causing the outer layers to expand. As a result, the sun will transform into a red giant, a phase where it will be hundreds of times larger and thousands of times brighter than it is today. The intensity of this transformation will be so great that the sun will engulf the inner planets, including our beloved Earth. But don't pack your interstellar luggage just yet. This event is so far in the future that it's almost beyond human comprehension. It's a future that serves as a reminder of the vast timescales on which the universe operates and the fleeting moment in cosmic history that humanity occupies. Following its red giant phase, the sun will shed its outer layers, releasing a stream of particles known as a planetary nebula. The core that remains will become a white dwarf, a dense, hot ember about the size of Earth. Over billions of years, this white dwarf will cool and fade, eventually becoming a black dwarf, an inert lump of carbon and oxygen. This is the ultimate fate of our sun, a transformation from a vibrant, life-giving star into a dim, cold remnant. It's a future that's both awe-inspiring and humbling, a testament to the grandeur and the impermanence of the cosmos. As we contemplate the sun's distant future, we are reminded of the impermanence of all things and the need to cherish our fragile planet. So let's savor the sunlight, feel its warmth, and appreciate the life it sustains. Because our time in the sun, just like the sun itself, won't last forever. In conclusion, The sun is more than just a star. It's a celestial marvel that has shaped our existence, from its formation and complex structure to its crucial role in sustaining life. Its cultural and scientific significance is profound, as are the captivating phenomena it displays. As we ponder its inevitable evolution, we're reminded of the ephemerality and preciousness of life. As we continue to learn about this radiant star, we deepen our appreciation for its role in shaping life as we know it.